Have you ever wondered how spell checkers or DNA sequence alignment tools work? They often rely on a fascinating concept called edit distance, also known as Levenshtein distance. It's a fundamental algorithm in computer science with wide-ranging applications. Imagine an ancient city named Lexiconia, where knowledge was preserved in grand, leather-bound spellbooks. In this mystical place, a royal scribe faced a significant challenge. She possessed two spellbooks, one old and one new, and her task was to meticulously rewrite the old book to perfectly match the new one. To achieve this, the scribe had three primary magical operations at her disposal. She could insert a new letter, much like using a magic quill to add a fresh rune to a page. She could also remove a letter, carefully erasing an old, unwanted rune. And finally, she could replace a letter, transforming one rune into another with a flick of her wrist. Perplexed by the sheer number of possibilities, the scribe sought wisdom from the wise oracle. The oracle, with profound insight, advised her, count the minimum number of these moves to make the old spell match the new. This was the core of her quest. The oracle continued, instructing her to fill a grid for every old and new position, decide inserting, deleting, or replacing what's cheapest. This was the key to her problem, a systematic approach to finding the most efficient path. By diligently following the oracle's guidance and meticulously filling her grid, the scribe finally uncovered the quickest and most efficient way to make the two spellbooks perfectly match. She achieved this by trusting the magic of dynamic programming, a powerful technique for solving complex problems. This ancient tale beautifully illustrates the concept behind the edit distance algorithm. In programming, we use a similar approach to quantify the difference between two strings, determining the minimum number of single-character edits required to change one word into the other. Let's dive into the Java implementation of this algorithm. We define a class edit distance, and within it, a public method minDistance that takes two strings, word1 and word2, as input. This method will return an integer representing the minimum edit distance. First, we determine the lengths of our two words m for word1 and n for word2. Then, we initialize a 2D array dp of size by. This dp array is our grid, just like the scribes, where we will store the minimum edits needed. Next, we fill the base cases for our dp array. For the first column, dpi 0 equals I. This means if word2 is empty, we need I deletions to transform word1 into an empty string. Similarly, for the first row, dp0, j equals j. If word1 is empty, we need j insertions to transform an empty string into word2. These base cases establish the starting points for our calculations. Now, we iterate through the rest of the dp array using nested loops, starting from I equals 1 and j equals 1. For each cell dpi, j, we compare the characters at word1.charat and word2.charat. If the characters are the same, word1.charat equals word2.charat, then no edit is needed for this position. So dpi, j, simply takes the value from the diagonal element, dpi1j1, meaning the cost is the same as the subproblem without these characters. However, if the characters are different, we must perform an edit. In this case, dpi, j, will be 1 plus the minimum of 3 possibilities, a deletion, an insertion, or a replacement. A deletion corresponds to dpi1j, meaning we delete the character from word1. An insertion corresponds to dpi-j1, meaning we insert a character into word1 to match word2. A replacement corresponds to dpi1j1, meaning we replace the character in word1 with the character in word2. After filling the entire dp array, the final answer, the minimum edit distance between word1 and word2, is found at dpm n, the bottom right corner of our grid. This cell holds the cumulative minimum edits. Let's consider an example, transforming kitten into sitting. The algorithm calculates the minimum edits. The main method demonstrates this, creating an edit distance object and calling minDistance with these words. The output for transforming kitten to sitting is 3. This means it takes a minimum of 3 operations, replacing K with S, inserting I, and replacing E with I to change the first word into the second. Each cell DPIJ in our grid represents the minimum edits needed to convert the prefix of word 1 up to index I, 1 into the prefix of word 2 up to index J1. This systematic breakdown is the essence of dynamic programming. The choices we make at each step, insert, delete, or replace, are crucial. By always selecting the option that yields the minimum cost, we ensure that we build up to the overall minimum edit distance for the entire words. The final answer, as we've seen, is always DPMN, encapsulating the solution for the complete transformation. This elegant algorithm provides a powerful way to compare and transform strings, with applications far beyond just spell checking. From bioinformatics to natural language processing, edit distance is a cornerstone. Understanding its principles, whether through ancient tales or modern code, equips you with a valuable tool for solving complex computational problems. Keep exploring the magic of algorithms.